I'm getting a B in this course. And if you're taking it, you know why. Greedy algorithms. A game like chess can be won only by thinking ahead. A player who is focused entirely on immediate advantage is easy to defeat. Are you sure about that? There are some, yeah, oh, maybe, chess though. You can frame your situation as a state, and then you just like you choose the action that maximizes your expected discounted sum of future rewards, right? And then that's greedy. So I don't know when this was written. No, he should know about that. But anyway, in many other games, such as Scrabble, it is possible to do quite well by simply making whichever move seems best at the moment and not worrying too much about future consequences. Scrabble? Yeah, but then you still have, so I've played this before, you still have to think about what words other people can make from the words that you make. So I don't think there's much of a difference between Scrabble and chess. This sort of myopic behavior is easy to and convenient, making it an attractive algorithmic strategy. Greedy algorithms build up a solution piece by piece, always choosing the next piece that offers the most obvious and immediate benefit. Although such an approach can be disastrous for some computational tasks, there are many for which it is optimal. The first example is that of minimum spanning trees. Suppose you are asked to network a connection of computers by linking selected pairs of them. This translates into a graph problem in which nodes are computers, undirected edges are potential links, and the goal is to pick enough of these edges that the nodes are connected. Okay. Yeah, so maybe not like computers, but routers, maybe switches. I know they're computers, but anyway, but this is not all. Each link also has a maintenance cost reflected in that edge's weight. What is the cheapest possible network? I see. So maybe like think of these as lengths of cable or something. And then that's an application of minimum spanning trees. One immediate observation is that the optimal set of edges cannot contain a cycle because removing an edge from the cycle would reduce the cost without compromising connectivity. Indeed. I believe you, so I'm just gonna skip this. This is not the only optimal solution. Can you spot another? So this thing costs 16. Is there another one that costs 16? Four. Maybe. I'll just believe you if you say it's not optimal. Kruskal's minimum spanning tree algorithm starts with the empty graph and then selects edges from the set of edges according to the following rule. Repeatedly add the next lightest edge that doesn't produce a cycle. That is a nice, concise way to put it. And it's like up to you to figure out how to do that. Okay. I'll skip that. The correctness of Kruskal's method follows from a certain cut property, in which is general enough to justify a whole slew of other minimum spanning tree algorithms. Cruscles. Let's see. So that's one. You get that one first. And maybe you would look for another one. But then you don't see any, so you look at this two. You could have picked this one, but I guess they picked this one. And then they looked at this. They see that it produces a cycle. I'll have to think about how to check for that. I know I've done this before, long ago. I just forgot. Maybe it's something to do with a union find kind of thing. Let's skip that. Figures. The cut property say that in the process of building a minimum spanning tree MST, we have already chosen some edges and are so far on the right track. Which edge should we add next? The following lemma gives us a lot of flexibility in our choice. Suppose edges X are part of an MST of G, this graph. Pick any subset of nodes S for which those edges does not cross between S and the difference between V and S, and let E be the lightest edge across this partition. Then the union of X, these edges, and the set of that edge is part of some MST. So, V minus S. So this thing's disconnected from whatever is spanned by X. And so, let's see, what is E? E be the lightest edge across this partition. So E connects these things. Then it must be some MST. Let's see. I believe it, but let me see what they're gonna say. A cut is any partition of the vertices into two groups, S and the difference between V and S. So like S and everything else. What this property says is that it is always safe to add the lightest edge across any cut. Provided X has no edges across the cut. I kind of believe it. Yeah, I believe it. See whether I really want to read this. Let me see what this says. What is this T prime thing? I guess I'll read it. Okay. Edges S apart from MST T. If the new edge E also happens to be part of T, then there's nothing to prove. But then it can't be. Yeah. We will construct a different MST prime containing that and this new edge by altering T slightly, changing just one of its edges. Add E to T. Since T is connected, it already has a path between the endpoints of E, so adding E creates a cycle. Within, yeah, this cycle must also have some other edge E prime across the cut. Let's see. I'm not quite getting that. This is an MST. E is part of this T. And then, okay, so it's not part of T. We'll construct a different one containing these edges and E, not part of these edges. Changing one of its edges. So how do you change it? It already has a path between the endpoints. Yes, somewhere. Okay, so it's not like going from some vertex in the tree to some vertex out of the tree. So it's making a cycle. And this cycle must also have some other edge across the cut. Where was this mentioned? Some MST of V, I guess. If we now remove this edge, we are left with T prime, which is like T with this edge without this other edge. And that's still a tree. T prime is connected by property 1. I wish I could click on these things. Okay. So what is this? Weight of this new tree is the weight of the old tree plus the weight of this new edge minus the weight of this old edge. I believe it. Now let's see what this is. Okay, that's a cut. S and V minus S. Here's this new edge we're considering. So the stuff without the dashed line is a tree. Did you say it's an MST? Yeah, it is. So this new edge and without this is not guaranteed to be an MST. But it's still a tree. Wait. Both E and E prime cross between these two partitions, and E is specifically the lightest edge of this type. Okay. So before, whoa. Yeah, wait. You said this is an MST? Okay. So E is less than or equal to this thing. And if the weight of this new thing is less than or equal to the weight of the old thing, then these two have the same weight. Yes, and so that's also an MST. Okay. Oh man. I don't know why they have to go through such lengths. Certainly not how I would have put it, but maybe it was necessary. Kruskal's algorithm. We are ready to justify Kruskal's algorithm. At any given moment, the edges it has already chosen form a partial solution, a collection of connected components, each of which has a tree structure. So at some point of Kruskal's algorithm, you got a bunch of trees. I bet they minimally span whatever they connect. Okay. We'll model the algorithm state as a collection of disjoint sets, each of which contains the nodes of a particular component. Initially, each node is in a component by itself. Am I going to have to make this set thing myself? Or can I just use a set? Anyway, create a singleton set containing just X. That's this thing. Test pairs of nodes, see whether they belong in the same set. Find X. Yeah, this is union find. You see, I don't forget everything. And whenever we add an edge, we are merging two components. Final algorithm is shown there. It uses the number of vertices, makes that, and 2 times the number of edges find, and this many union operations. Okay. Connected undirected graph with some weights. They can be negative or whatever. Minimum spanning tree defined by the edges. So first of all, put all the vertices in their own set. And then X is this empty array of edges. Sort the edges by weight, and then for all edges, in increasing order of weight, if the two vertices are not in the same set, add the edge to the set of edges in the MST, and then merge these two sets. Okay, so it's like number of edges, of number of edges. What is this though? Maybe it's like log of something. But then I can at least say it's O of number of edges. A data structure for disjoint sets. Union by rank. One may store set. One way to store a set is as a directed tree. Directed tree. Yeah, okay. So like a, no. Yeah, directed tree, fine. Nodes of the tree are elements of the set arranged in no particular order. And each has parent pointers that eventually lead up to the root of the tree. This root element is a convenient representative or name for the set. So I'm thinking log of something. Make set is constant. Find takes time proportional to the height of the tree. And the tree is built by union. So you have to make sure union keeps trees shallow. Okay. Make the root of the shorter tree point to the root of the taller tree. So the height increases only if the two trees being merged are equally tall. Huh? Equally tall. The root of the shorter tree, okay, then it increases by 1. Instead of explicitly computing heights of trees, we'll use the rank numbers of the root nodes, which is why this scheme is called union by rank. Let's see. Union. You get the rank of X, rank of Y. I'm assuming R is rank. And then if they're in the same set, basically you return otherwise. If the, I guess this means root. If the rank of the root of X is greater than the rank of the root of Y. What is pi thing? A parent of the root of Y is the root of X, which makes sense because in this case you don't increase the rank. Yeah. Otherwise, if they're equal... Oh, no. Otherwise, like, if they're equal, then they're in the same set, right? No? Well, that makes sense. Let's read this. If the rank of the root of x equals the rank of the root of y, I see. So this is, if they're the same root, they're in the same set, return. If they're unequal, you do this. I wish they would, like, unindent this and say else if. Or just, like, unindent it. The rank of the root of y is the rank of the... Okay, you add 1. Okay, so you just make y the parent and then increase its rank by 1. I see. So I know why this is indented now. Sorry for being dumb. By design, the rank of a node is exactly the height of the subtree rooted at that node. Okay. This means, for instance, that you move up a path toward the root node, the rank values along the way are strictly increasing. I super don't want to write this. Maybe it's not as hard as I think. This sort of thing that should just be built into languages. Path compression. With the data structure represented so far, the total time for Kruskal's algorithm becomes... Yeah, that's what I said. So, number of edges multiplied by log of number of vertices. For sorting the edges... Oh, for sorting the edges... yeah, and that also for the union find operations. So why make it more efficient? What if the edges are given to us sorted, then we can do this in linear time? Wait, so this thing... Maybe using a heap of some sort? By being a little more careful to maintain our data structure in good shape. Blah. This path compression heuristic only slightly increases the time needed for a find and is easy to code. What is this? If x is not its own parent, so if x is not a root, the parent of x is find. So when you look for the set of any vertex at the same time, you just like assign its parent. So it's just like name it. So then you like opportunistically shorten the tree. Like, intuitively, I believe this amortized cost thing, but I forgot how to calculate it. Okay. We now know that the ranks of root nodes are unaltered, but what about non-root nodes? Yeah, I know. Let's move on. Okay, I forgot log star. Log star. They're totally gonna quiz me on this. If there are n elements, the rank values can change from 0 to log n by property 3. Forgot what that was. Let's divide the non-zero part of this range into certain carefully chosen intervals for reasons that will be soon become clear. Each group is of the form k plus 1, k plus 2, all the way to 2 to the k, where k is the power of 2. So something like, yeah, so 1, 2, these two. So, yeah, 4 to 16, 17 to what now? 5, so 32 numbers in here. And then 64 in the next. Oh no. 32. This goes to 2 to the 16. K is a power of 2. So this is 0, 1, 2. All the way to 2 to the K, 2 to the 0. Okay. So I get it. So 2 to the K, 0, 1, 2, 3. This goes. Huh? Oh no. This is 1, right? No, this is 1. Oh, the web to 2, okay, this is 2. 0, 1, 2. Why is this not 3? Maybe there's a typo. Let's move on. Specifically, we will give each node a certain amount of pocket money. Such that the total money doled out is at most n log star n. Do I need to look up this log star thing? Yeah, give me a sec. I need to look it up. So sorry you can't see this, but the iterated logarithm of n, log star n, is the number of times the logarithm function must be iteratively applied before the result is less than or equal to 1. So, what does this mean? Okay. So, they're not writing a base, probably because it doesn't matter. Or because it's 2. People do different things. If it really must be 2, I think they write 2. And this star, it's like the number of logs that you apply. So maybe, I don't know how you would put it. Maybe like the inverse log iteratively of 1. I don't know. I get it though. Like, how do you come up with this? At most n log star. In dollars, we will show that each find takes log star of n steps. which is like plus some additional amount of time that can be paid for using pocket money of the nodes involved. Okay, I need to look at Wikipedia some more, because I know they're gonna screw with me with this. I'm getting a B anyway, despite all my efforts. Let's see. Log star of n is defined as 0 if n is less than or equal to 1. Oh, it's like recursively. And if it's greater than 1, it is 1 plus the log star of log n. So let's do an example. Let's say n is 4. So log n is 2. Log star of that. So it's, yeah, log star of that is log star of 2. So then it's like 1 plus log star of 2, which is 1. So then we're going back up. No, not yet. Log of 2 is 1. And then you do log of 1, which is 0. Okay, now we're going up the recursion. Okay, 0. Plug that into here. 1. Okay. So, okay. Oh, I see some examples. Log star of x between negative infinity and 1 is 0. Okay, so that's what these intervals are. Log star of, like, this is 1. Let's see, 4, 16. 4 to 16, so if that is 3, if this is 4, if this is 5. Okay, I got it. So it's basically, it's almost free. Let's see, now it's time taken, find. Okay, so it's like almost linear. You just get this right though, because I bet if I say it's linear, they're gonna screw me. It's log star of n to do this. Okay, this only works if the initial allowance of each node x is enough to cover all of its payments in the sequence of find operations. I'll read that carefully later. Prim's algorithm. Let's return to our discussion of minimum spanning tree algorithms. What the cut property tells us in most general terms is that any algorithm conforming to the following greedy schema is guaranteed to work. X is the edges picked so far, repeat until the number of edges picked so far is the number of vertices minus 1, which is the number of edges in the minimum spanning tree, right? I forgot. I think it is. Pick a set S, a strict subset of the vertices for which X has no edges between S and everything else. Let E, an edge, be the minimum weight edge between S and everything else, and then add it to X. So how's this different from Cruscles? Maybe this is not prims. Oh, maybe it is. Let's keep reading. Popular alternative to Kruskal's algorithm is prims, in which the intermediate set of edges x always forms a subtree, and S is chosen to be the set of this tree's vertices. S, okay. Of each iteration, the subtree defined by x grows by one edge, namely the lightest edge between a vertex in S and a vertex outside S. So it's kind of like Kruscals is like you just put stuff everywhere, the minimum edge anywhere, and prims is like you keep the whole thing connected as one and just grow that thing. How about disconnected graphs, though? I guess there's no minimum spanning tree of disconnected graphs. Yes, you find the minimum weight of all the vertices in S, the minimum weight of man. Yeah, it looks like Dijkstra's algorithm. And in this algorithm, you can keep a priority queue or something. Okay. Prim's algorithm. Okay. Minimum spanning tree. This is an illustration of Prim's algorithm starting at node A. Also shown are a table of these values. Well, let's just read this. For all U's vertices, initialize the cost of U to infinity and the previous to nil. Pick any initial node U0. Say that the cost of U0 is 0. So this is Dijkstra's the same. H. Make a priority queue out of the vertices using cost values as keys. So it's like infinity except the starting one, and while U is not empty, pop it from the priority queue for each edge going out of that vertex if the cost of the vertex is greater than the weight from there. You update it, you say the previous, and then you decrease the key. Decrease the key in this priority queue of this. I think I know what this is, but maybe we should look for it. Where's decrease key? Decrease key. Maybe he didn't write about that, which is fine. I can pretty much guess what that is, so I'll forgive him. Huffman encoding. Isn't this like a dynamic thing? Yeah, just gonna skip most of that and read this. Let's see. F is an array of frequencies of symbols, and you output an encoding tree with n leaves. Let me get a drink. Okay, so H is a priority queue of integers ordered by frequency, huh? Why is it a priority queue of integers? Maybe they're indices. For I in 1 to n, insert into the priority queue this integer. So it's like enqueuing everything ordered by frequency. I'm assuming integers are symbols then. I hate how... Let's just keep reading. Maybe it'll become clear. For k in n plus 1 to 2n minus 1, what do we do with this k? Pop it, and that's I, j. Oh, you pop twice and you got I and j. So you've got these like minimum frequency things. Create a node numbered k with children ij. K is n plus 1 to 2n minus 1. And then the frequency of k is the frequency, the sum of these frequencies, and you enqueue these things. Yeah, I can see that. So you want lower frequency things in deeper parts of the tree. Got it. And is that any better than a certain greedy algorithm? Not greedy, dynamic algorithm that we can think of, probably. Seem to remember something about matrix multiplication. Well, Huffman encoding. Let me see the runtime of this thing. N log n. If a heap is used, so it is actually better. Nice. Horn formulas. In order to display human-level intelligence, a computer must be able to perform at least some modicum of logical reasoning. I mean, there are gates. But higher than that, I wouldn't make that claim. Do you think we do logical reasoning? We might look like we're doing it, but it might be just a bunch of probably approximately's. You can still fail. I fail a lot to make sense. This is too strong. But anyway, it's not important. Horn formulas are a particular framework for doing this, for expressing logical facts and deriving conclusions. The most primitive object in a Horn formula is a Boolean variable. Okay. Taking value either true or false. For instance, variables x, y, and z might denote the following possibilities. X is, the murder took place in the kitchen. Some Boolean value. Wait, why use this? A literal is either a variable x or its negation not x. In Horn formulas, knowledge about variables is represented by two kinds of clauses. Implications, whose left-hand side is an and of any number of positive literals. So it's like you can big and of a bunch of stuff, huh? and whose right-hand side is a single positive literal. These express statements of the form, if these conditions, then this other thing. Fine. Pure negative clauses consisting of a bunch of ors of negative things. They can't all be, so it's like not this or not that or not that. Why must they be expressed this way? You could, like, can we take this and out? And then we take this not out? Yeah, they can't all be in a... So you can say not big and of all these things. Well, let's keep reading. Given a set of clauses of these two types, the goal is to determine whether there is a consistent explanation, a satisfying assignment. Yeah. The two kinds of clauses pull us in different directions. The implications tell us to set some of the variables to true, while the negative clauses encourage us to make them false. So if one of these is false, we satisfy this. If, wait, what did you say? What? Why is this encouraging us to make them all make some of them true? Some of the variables to true. Why not all of them? Maybe these? Fine. In other words, our algorithm for horn clauses is the following greedy scheme. Stingy is perhaps more descriptive. Well, you use one word, you use it consistently. This is a horn formula. Let me just make sure I know what this is. Okay, it's a set of this and that. A satisfying assignment if one exists. Set all variables to false while there is an implication that is not satisfied. Set the right-hand variable of the implication to true. If all pure, so then at the end of this thing, all of the things on the left side of the implication are true. And then if all pure negative clauses, so the second thing in the set, return the assignment, otherwise it's not satisfiable. So, why is this not O of 1? Oh, it's a bunch of things. So it's not just a set of two things, it's that these bunch of implications and this bunch of nots. So then I see, so set all these to true. It should be linear. Set them all to true, true. Nothing? X must be true on account of the singleton implication. I've never seen that before. Maybe it's like assert. Assert X. Then we see that Y must also be true because Y, X implies Y. There. Okay. So then maybe Is there a possible way to not satisfy the implications? No. It's only when you check these. Notice that if it returns an assignment, this assignment satisfies both. So we only have to convince ourselves that if the algorithm finds no satisfying assignment, then there is none. Yeah, that needs a bit of thinking. If a certain set of variables is set to true, then they must be true in any satisfying assignment. So the hard part is probably putting your situation in such a formula. What's prologue? Programming by logic. Some electrical people use this. Okay. Set cover. The dots in this figure represent a collection of towns. Each county is in its early stages of planning and is deciding where to put schools. What is this figure? 5.11, okay. There are only two constraints. Each school should be in a town. Each school should be in a town, and no one should have to travel more than 30 miles to reach one of them. No inhabitant should have to travel. What is the minimum number of schools needed? So it's like, where do you put your access points, your Wi-Fi access points, right? For each town, let S be a set of towns within 30 miles of it. A school at X will essentially cover these other towns. Town X, S of X, or SX is a set of towns within 30 miles of town X. I see. So SX is like the neighborhood of X. A school at X will essentially cover these other towns. The question is then how many SX must be picked in order to cover all the towns in the county? A selection S whose union is B. B is what now? Maybe vertices? The elements of B are the towns. Just look. So we got a bunch of vertices. So I'm imagining we have edges between each vertex and each other vertex. So this whole thing's dense. Let's see. Repeat until all elements of B are covered. Pick the set Si with the largest number of uncovered elements. What is I? The set with the largest number of uncovered elements. I don't find it extremely natural and intuitive. The goal was to cover stuff. And then you're saying pick a set. Well, let's see what it would do in our earlier example. It would first place the school at town A. Oh, I see. Until they are covered. So some are covered and some are not. You pick a set that turns uncovered elements into covered elements. That's not optimal. But it's not too far. Suppose B contains n elements, and that the optimal cover consists of k sets. Then the greedy algorithm will use at most k natural log of n. What is this? You need to explain. Yeah, well, I know what that means, but like, let nt be the number of elements still not covered after t iterations of the greedy algorithm. Number of elements. So n0 is n, and n once you are done is 0. Since these remaining elements are covered by the optimal k sets, remaining elements, so what is this k? That the optimal cover consists of k sets. So like magically you know k, then the greedy algorithm will use at most k times the natural log. So this is an upper bound, huh? Yeah, I believe you. Huh? We call this maximum ratio an approximation factor. There seems to be a lot of room for improvement, but such hopes are unjustified. It turns out that under certain complexity assumptions, there is provably no polynomial time algorithm with a smaller approximation factor. So you can prove that there's no polynomial time algorithm in chapter 8. That is unexpected. Is that cover? Is that hard? I'm gonna look at this later. That's a word I didn't expect to see here. Exercises. That's a graph. What is the cost of its minimum spanning tree? Let's use Kruskal's. 1, 2. Let's do that one. 4. Let's do that one. 7, 10. Now I'm losing track. 14. Did I do this one yet? That would make a cycle, so wait, yeah, I can't remember. I need to do this on paper. How many minimum spanning trees does it have? Interesting. How would you even do that? I guess each time there's a tie, you can count that and just multiply it. So like, you look at these two, and then you're like, hey, I can make a tree using this edge or this edge. So let's, no, that's not gonna work. Right? No, it's still fine. Because you're still gonna look at every edge. So then it's like, okay, I just pick this one. And then I ignore that one. When I see the twos, I see, okay, there are 2 of them. I can make a tree out of this or with that. Just multiply it by 2. Suppose Kruskal's algorithm is run on this graph. In what order are the edges added to the MST? For each edge in this sequence, give a cut that justifies its addition. Well, in increasing weight order, but a cut. So we start with something. Nah, let's not say that. Just start with some edge, like that one. Pick a vertex and say that's some part, and then the rest of it is the other part. That's a cut. Once we add this, this will be like your partition, and then this the rest of it. No, that's not what they're asking. You can just have any cut, right? It doesn't have to be like connected yet in a tree. Let's move on. Suppose we want to find the minimum spanning tree of the following graph. Run Prim's algorithm. Whenever there is a choice of nodes, always use alphabetic ordering. Draw a table showing the intermediate values of the cost area. I don't feel like it. So we would start here because it's the letter A. And then like for each edge out of this blob, we add the minimum one. So we add this one. So we got A and B. For each edge out of this blob, we add the minimum, which is 2. So we now have A, B, C. And the minimum out of that is 2. A, B, C, G. And then we got these ones. So we're going to pick F. And then we will pick D. H. And finally E. From here, A to E. Draw a table of the intermediate values of the cost area. Yeah, I know how to do that. Run Kruskal's algorithm. Show how the disjoint set's data structure looks at every intermediate stage. I could. I don't feel like it. Design a linear time algorithm for the following task. A connected undirected graph. Okay. Is there an edge you can remove from the graph while leaving it connected? So is there a cycle? Is there a cycle? Just BFS in linear time. Can you reduce the running time of your algorithm to a number of vertices? Look for a cycle in time order of number of vertices. I'll think about this for like 30 seconds and then Google. So I offered something number of vertices plus number of edges. How can I just ignore the edges? If I had... if I put them in some kind of union find... That's still not, unless they're being sloppy about this. Okay, let's Google. Okay, I think this is important. I see. What is this? Here, Holzer's algorithm? Finding cycles in number of edges. What is this? Eulerian path is a trail and a finite graph that is no, that's not what I'm looking for. Algorithms. Fast and slow. I have seen this before. I have seen it before, but I forgot what it was. Why are you asking me this in a textbook? I mean, in this textbook without just telling me. It was hard enough to come up with that it has somebody's name on it. Yep, anyway. Show that if an undirected graph with n vertices has k connected components, then it has at least n minus k edges. Undirected graph, n vertices, k connected components. That's like k connected graphs. Then how many edges does it have? At least undirected graph, n vertices, k connected components. What if k is n? It's just a bunch of vertices disconnected, but each connected to itself. Then it has at least n minus k. Yeah, it has at least 0 edges. What if, let's say we got 2 components, 3 vertices and 1 component is connected by an edge. So 3 minus 2, it has at least 1 edge. How would I show that though? Maybe you say something about the number of tree edges is exactly number of vertices minus 1. And you got k connected components. So something about being disconnected. I don't know. I can think a bit about it later. Consider an undirected graph with non-negative edge weights. That's probably important. Suppose that you have computed an MST of this graph and that you have also computed the shortest paths to all nodes from a particular node. Suppose each edge weight is increased by 1. The new weights are that. Does the minimum spanning tree change? Give an example where it changes or prove it cannot change, and then do the shortest paths change. Can I come up with an example where this thing changes? Oh, non-negative. Wait. Non-negative, but still, if you increase stuff by 1, the shortest paths, the order We got some MST. So you know the MST. If you change the weights, the order of the edges that you add, if you make an MST, doesn't change. So the MST doesn't change, but do the shortest paths change? Can I come up with an example? Non-negative. It can be. Yeah, what if they were all 0? They were all 0 before, so you just pick any path, and that's the shortest paths. But then if you increase them all by 1, there you can also pick any path. I don't know. Later, let G be a graph undirected. Prove that if all its edge weights are distinct, all edge weights, then it has a unique minimum spanning tree. There is one order. There's one way to sort the edges of this graph, since they're all distinct. And to make the minimum spanning tree, you'll add these edges in increasing order. So there's only one order in which to add them. So there's only one MST you could build. Okay, let's see what else there is to do. What is this 5.9? Let's look at that one. There are a lot of exercises on these greedy algorithms. Nine. It's like true or false. In each case, either prove it or give a counterexample. Always assume that the graph is a set of V and E, undirected, and do not assume that edge weights are distinct unless they are specifically stated. Okay. If graph G has more than V minus 1 edges, number of vertices minus 1, then, and there is a unique heaviest edge, so one edge has the greatest weight, then this edge cannot be part of a minimum spanning tree. I think that's true, and I can prove it. So the edges in the graph are not a tree, since there are more than this many. So there is some edge that is in a cycle. Wait. But then this unique heaviest edge might not be in such a cycle. So I can give an example. Let's make a triangle with one thing sticking out of it. So the triangle is a cycle, and the one thing sticking out of it has a heavy edge. So you can kill one of the edges in the triangle, and then it'll be a tree, and there's no other way to get to that one vertex outside of it besides this heaviest edge. So that's actually false. That was tricky. I mean, tricky to me. Okay. If G has a cycle with a unique heaviest edge E, a cycle and E is in the cycle, then E cannot be part of any MST. Yeah, an MST will kill the cycle. And if you're going to kill the cycle, you might as well remove the heaviest edge. Actually, that's the only way to do it, to make the MST. Hey, come to think of it, is there a different way to make MSTs? Let's say you have all the edges in the graph already, and then you look at all the cycles, and then you remove the heaviest edge. Is that a way to do it? Anyway, I think that's true. Let E be any edge of minimum weight in G. Okay, E is an edge of minimum weight. Then E must be part of some MST. So E is one of those. Part of some MST. So yeah, if you're making it, you're considering one of those minimum weight edges. They're at the top of your heap or whatever. You might choose E. If the lightest edge in a graph is unique, the lightest edge, then it must be part of every MST. That's true. If E is part of, well, I have to prove it. It is unique. It is the lightest. Once you make your MST, you're gonna choose it. If E is part of some MST of G, some MST, then it must be a lightest edge across some cut of G. Must be a lightest edge across some cut of G. I think by definition that's true. So let's cut G across this lightest edge. I mean, it speaks for itself. I don't know. Maybe someone smarter can prove it better. If G has a cycle with a unique lightest edge, E, then E must be part of every MST, huh? A cycle. To make the MST, you're gonna kill the other edges in the cycle besides this one. Unique. Yeah. I'm sick of proving it. Just accept it. Nah, I have to. Yeah, but that's what I said. You're gonna kill some edge. You're gonna kill some edge that isn't this one. The shortest path tree computed by Dijkstra's algorithm is necessarily an MST. Really? It is the shortest paths from somewhere to everywhere else. Can I give a counterexample? Maybe. I think this is false. But I need some paper or time to come up with a counterexample. Let's see if I can. Give me like 30 seconds. What if there are 3 vertices? You start in the middle. No. What if there is a square or quadrilateral? You start on some corner. And let's say it's like all of the edges are 1 except for one of them. So it's like 1, 1, 1, 2. The shortest path. Yeah, I came up with an example. Okay, so it's like a quadrilateral with edges 1, 1, 1, and 2. It's a, yeah. And you start on some vertex, the shortest path to an adjacent one, like some vertex with the 1 edge and the 2 edge. You go across the 2 edge to get to that other vertex, but the minimum spanning tree doesn't contain that 2 edge. Okay, the shortest path between 2 nodes is necessarily part of some MST. No, that's what we just said. Yeah, I gave a counterexample. We can use that same counterexample. Prim's algorithm works correctly when there are negative edges. I forgot. I think so. Yeah, you're still adding, like, for every edge you're still getting the minimum. It's not like you're trying to keep yourself from going in circles just to save money or save weight. What is this? For every r greater than 0, an r path is a path whose edges all have weight less than or equal to r. R path. So it's like no step you take in this r path is as expensive as r. If G contains an r path from S to T, then every MST of G must also contain an r path from S to T. So if there's a path whose every edge is upper bound strictly by R, then every MST must contain an R path from S to T. Well, let's see. So, can I come up with an example where there's a path that is upper bound by some constant? Yeah, whose every edge is upper bound by some constant, but the MST, there is an MST that does not contain a path that is upper bound by that same constant. Oh, from those, yeah, a path between those same nodes. I can't come up with any. I'm just thinking about my quadrilateral example from before. Let's say S to T is across that 2 edge. I can say R is like something greater than 2. But then the tree also contains an R path, because all the 1s are less than something greater than 2. Can I prove it? Maybe with using the priority queue, sorting the edges. I think it's true, but I'm not going to prove it here. Let's end soon. Let's look for something that looks interesting. What is this? We will develop a new algorithm for finding minimum spanning trees. It is based upon the following property. Pick any cycle. Let E be... That's what I said before, right? Let E be the heaviest edge in that cycle, and then there is a minimum spanning tree that does not contain E. Prove it. No. What's the rest of this say? Here is the new MST algorithm. The input is some undirected graph in adjacency list form with edge weights. Sort the edges according to their weights. For each edge in decreasing order. If E is part of a cycle, remove E from the graph and return this graph. Prove it's correct. Okay, what's this say? On each iteration, the algorithm must check whether there's a cycle containing a specific edge E. Give a linear time algorithm for this task. Justify its correctness. Given an edge in linear time, check whether it is in a cycle. You can BFS in linear time. You might be able to do better. What is the overall time taken by this algorithm in terms of number of edges? Explain your answer. If you're gonna do that, let's see, sort the edges. That's like number of edges, log number of edges. For each edge in decreasing order, if E is part of a cycle, so probably number of edges squared, and then remove E from G. It's constant time. Yeah, because this squared thing dominates this log thing. Okay. Can I prove it's correct? Well, first prove this. If it's in a cycle, the minimum spanning tree will not contain some edge in the cycle. And since it's going to have, since it's minimal, it's not going to pick this heaviest edge in the cycle. It's going to pick something else. Let E be the heaviest edge, so it is uniquely the heaviest edge, so it's definitely not going to pick E. I don't know if that's carefully enough for these authors, though. No matter what I do, some TA is gonna not read it correctly and then mark me wrong. Now prove it's correct. Let's see. You have sorted them in decreasing order, and you're going to check whether they're in a cycle. Until you have looked at every single edge and so if you look at all edges and if they're in a cycle you remove them, then you're going to remove all the cycles. And if you remove, and in each cycle you're definitely going to remove the heaviest edge since you sorted them in decreasing order from the before. Or you're going to remove a heaviest edge, which is good enough if it breaks the cycle. Okay. Yeah, so let's end here and do our homework.